These programs use bilinear interpolation. This forces restrictions on where you can specify your velocity or mute functions. These restrictions are explained in this video. But Delaunay triangulation allows random locations. So why did I choose bilinear rather than Delaunay? It's because I've used Delaunay before for interpolation purposes. Delaunay triangulation often produces sliver triangles, which are long, thin triangles along the edges of your specified velocity locations. The effects of sliver triangles is often subtly bad, and subtly bad is the worst kind of bad in seismic data processing. Now, I have nothing against Delaunay triangulation. I've used it myself for interpolation in other seismic data processing systems that I programmed for. But I believe that bilinear is what Seismic Unix should start with for 3D. And the good thing about programming for Seismic Unix is that I get to decide.
Generally, this video consists of diagrams and screenshots which I talk over. The video is a general overview of 3 bilinear interpolation programs. These programs have extensive tests in the demos directory. Some of those tests are easy to understand, some are not. Generally, I try to put in an image that indicates the start of a new subject, like this one. Bilinear interpolation is well known, so I won't review the arithmetic. But bilinear is, of course, just linear interpolation in one direction, followed by linear interpolation in the other direction. It does not matter which direction you interpolate first. Also, I'm going to use the words vertical and horizontal. In 3D, you usually use words inline and crossline, but vertical and horizontal are clearer here. For bilinear interpolation, the vertical and horizontal position of a point P is compared to the widths of the rectangle that surrounds it. This produces weights to use while summing the values of the 4 points. If your point is outside the rectangle, then you can choose to use a combination of linear extrapolation in one direction and linear interpolation in the other. But note that extrapolation options are not available in Sunmocsv. This conforms to how the 2D Sunmo program works. That program does not allow extrapolation. Or, if your point is outside the rectangle, you can choose to not extrapolate in that direction. Effectively, this means that the interpolated value is the same as if point P were located exactly at the nearest point along that side of the rectangle. Remember that vertical interpolation is still occurring. So every point at right angle to that side gets the same value as the closest point on that side. You can use various terms for the next concept: enclosing rectangles or aligned rectangles or surrounding rectangles. In the examples, I use the 3D grid defined in the demos directory. But all you really need to know here is that it has 121 cells in the horizontal direction and 23 cells in the vertical direction. The CDP numbers start at corner A and increment horizontally across to corner B, which therefore has CDP 121. The numbering then continues from 122 at the next vertical cell upward from corner A. Let's start with the simplest possible bilinear case, which is 4 points. We'll come back to what happens if you have less than 4 points. Note that these 4 points must form a rectangle. Knowing the dimensions of the grid are 121 by 23, you can quite easily figure out which CDP number combinations you can specify. Later in this video, there is an example of how to automatically get nice CDP numbers for velocity analysis semblance scan locations. So the area within these 4 points will use bilinear interpolation of the values at the surrounding 4 points. Usually the simplest thing to do is specify CDP locations at regular spacings. This produces enclosing rectangles that have the same size. This is convenient, but may require more of your time than necessary. For instance, when deriving velocity functions, you do not want to perform more VLAN semblance scanning than necessary. This image shows CDP locations which produce different size rectangles. So you can still provide more velocity or mute functions in areas where they are needed, while spacing the functions wider in less critical areas. To try to be completely clear, this image highlights areas where linear interpolation will occur in one direction, and also linear extrapolation in the other direction if that option is used. This image shows areas where bilinear extrapolation can occur, or linear extrapolation in one direction, or no extrapolation, in which case the value is the same as the corner value. There are some special situations. If you specify only one point, then you get its values everywhere. You can also specify any number of points along one cell line. For this, you get linear interpolation in that direction. All locations get the same value as their right angle location along the line. Note this means the Sunmocsv program can also handle 2D surveys, which is why it allows you to not input a 3D grid definition. You can see the documentation of Sunmocsv later in this video. Okay, let's get to some actual setups for bilinear interpolation. You are probably more interested in velocities and NMO, but examples that use the Sumutecsv program make easier to understand trace displays. We'll see some setups of Sunmocsv later, and you'll see they are similar to the Sumutecsv setups. Most tests shown here use SUNull to create fake traces. Then every sample in all those traces is set to amplitude 100. The CDP numbers in those traces are set so that we only get one cell line. The offset value in all those traces is set to a constant value. When the mute is applied, it zeroes some of the samples. This makes a clear display of what the interpolation is doing. Here, the SUNull program is creating 121 traces. The SUMath program is setting all amplitudes in those traces to 100. The SUSetHeaderWord program is setting the first CDP to 1211 and incrementing by 1, and also setting the offset to 500 for all traces. The Sumutecsv program is inputting those traces and a 3D grid definition, and specifying 4 CDPs and the offsets and times at those 4 CDPs. The option to extrapolate is seen in the orange ellipse. In the left display is the result with no extrapolation. In the middle of the left display, you can see a linear trend, as you should expect from this situation. Remember that the vertical position is constant here. So the vertical part of the weighting will be the same for all points along the cell line. And note that the ends of the left display become constant because there is no extrapolation. On the right is the display using the extrapolation option. Same kind of example, except along a vertical cell line. The CDP numbers for this vertical cell line start at 60 and increment by 121 because the grid is 121 cells wide. And remember that this grid only has 23 cells in the vertical direction. Same mute setup, except the extrapolation parameter is for the vertical direction. Note the letter C on the end instead of I like the previous setup. These letters stand for inline and crossline, which are familiar terms in 3D, even though they are not rigorously defined. Similar results as the previous horizontal line test. Now we are switching back and using a horizontal cell line again. only this time we're going to have two enclosing rectangles. Same setup as before, except with two additional mute functions. Note the left display shows two linear trends near the middle and then becomes constant at both ends. In the right display, the ends extrapolate as expected. This setup is the same as the previous setup for two enclosing rectangles, except that the mute functions are input from a Q file. The Q file is shown at the bottom. The Q records contain a CDP number followed by offset time pairs. Note the names on the second record are the same as the names of the parameters, which are CDP, offs, and tims. Also note that the offs and tims names repeat once. This is how Q files say that varying numbers of pairs exist in the Q records. The complete Q file standards are shown later in this video. You can also extrapolate in the tertiary direction. For offset time mutes, this means you can extrapolate for trace offsets less than the lowest offset in the mute function and higher than the highest offset in the mute functions. Same setup, except setting all trace offsets to 200 instead of 500, and using the parameter that controls tertiary extrapolation. Okay, all you can really see is that it is different for extrapolation versus no extrapolation. But my tests in the demos directory indicate that all this works as intended. You are welcome to run those tests and confirm that yourself. Okay, you've waited long enough. Now for some SU-NMO-CSV setups. Looks pretty much like a SU-mute CSV setup except for the parameter names. That should not be a surprise. After all, SU-mute CSV uses offset time pairs at CDPs, and SU-NMO-CSV uses time velocity pairs at CDPs. This setup is actually copied from the tests in the demos directory. Those tests create a full 3D survey worth of fake traces and apply this NMO correction to those traces and stack them. Here's the same thing, but using a Q file to input the velocity functions. Again, except for the names, it looks like the Q file for SU-mute CSV. The SU-binQ CSV program can input the parameters of both the SU-mute CSV and SU-NMO CSV programs, and bilinearly interpolate their values and output them into another Q file. Remember that Q files are CSV files, so there are a lot of programs that can read them, including spreadsheet programs. This is SU-binQ CSV inputting the velocities just seen in the previous SU-NMO CSV setup. The out-end parameter is telling this program to output interpolated velocities at 100 millisecond intervals. The IEcho parameter says to only output Q records at the same CDP numbers as our input. Other options allow you to output Q records for every CDP in the entire 3D grid. This variant of Q file puts the time values in one record. You can see the times on the record which starts with C_SU_ dims. The Q records themselves contain the velocities at those times. You can also see the CDP numbers at the front of those records. The output Q records also automatically get some values computed from the 3D grid definition. Perhaps the most notable of those values are the XY coordinates. The grid IGI and IGC indexes are also output. Both the coordinates and the indexes give you values that allow you to plot the velocities. The SU-binQ CSV program also gives you an easy way to get CDP numbers that make enclosing rectangles. The IGI out and IGC out parameters allow you to output a subset of the 3D grid CDPs. They also come in handy to generate CDPs for mute locations or VLAN locations. VLAN, of course, stands for velocity analysis, typically done using semblance scans. Now, At this point, I should tell you that I have not yet actually tried to run VLAN analysis for 3D in Seismic Unix. In theory, semblance scanning should work fine since it uses the offset distances within a CDP gather. So it should not care that the traces in a 3D CDP have wildly varying azimuths. But the programs involved may get entangled since they believe the CDP numbers are located along one line. I expect to try making VLANs after I finish this crop of videos.
That about covers what I wanted to say today. The rest of this video includes Q file standards and documentation of the programs discussed today, just so you don't have to go looking for it in the demos directory of Seismic Unix or by outputting the documentation that comes with the programs themselves. The general idea of Q files is to allow spreadsheets to deal with situations where a large amount of parameter values need to be handled. Spreadsheet programs know how to make plots and displays and analyze these values. This relieves a lot of that effort out of the Seismic Unix programs and simply transfers it to something that already knows how to do all that sort of stuff.
Next, look at Q file standards. Q files are just something I made up in 2021. Notice that there are some records at the top which start with C and _SU. The SU stands for Seismic Unix, of course. These C_SU records are also used by programs SU-geom_CSV and SU-tool_CSV. Some forms of Q files can be read by SU-geom_CSV and SU-tool_CSV, although these programs usually deal with SPS geometry files. The initial C exists on these records because many programs will consider them as comment records and ignore them. This is desirable since these files might be input to programs unrelated to Seismic Unix. The only other thing I want to mention is that these standards refer to tuples. That word is the generic term for pairs or triplets or quadruplets of values. So offset time pairs are two tuples, and time velocity pairs are also two tuples. The only extra I want to say here is that the check and print options can be quite useful. You can see here that there are no extrapolation options. Again, the check and print options can be quite useful. In this video, you have already seen an example of Subinqcsv inputting velocity functions and outputting velocities at specific time increments. Alternate parameter outlist allows you to output at specific times. I also draw your attention to the INVP2 parameter. This parameter allows you to tell this program to treat the input like velocities. This involves weighting based on the inverse square of the values themselves. Note that this is not inverse square of the distance between locations. This weighting is what SU-NMO and SU-NMO-CSV do. The default in Subinqcsv is to use that weighting for all names that start with the letter V, which includes the velocity name for SU-NMO-CSV.
You may find my videos dry and boring, but remember, I'm not trying to sell you anything. Seismic Unix is open source, and I have no intention of becoming a YouTube star. I really just want to get back to programming, but I feel the need to cobble together some videos